So where we left off, we were looking at different types. We had talked about different types of waves last time. So let me go back a couple things here. We'd ended with a review of longitudinal and shear wave, and we talked about that with the slinky example, right? So we're going to use longitudinal waves for most of what we're going to be doing. What you're going to be, everything you do in lab that's not self-designed is going to be transmit, receive, or what they call pitch catch or pulse echo mode of testing. But there is also angle beam, and in angle beam testing, that's where we're going to use that shear wave property. And so we're going to send that sound in at an angle, and it can bounce off of things that are kind of each side of that wave to find it. One last one, I showed you a video. We talked about surface waves, and it's a specialized form of angle beam testing that's shown here. And so this is a surface wave, and it's designed for finding surface cracks along the length of an object. And so we send the sound in a longitudinal wave at a very shallow angle, right? So we try to get it as parallel as possible to the surface of the material. And it's going to cause a wave, a single wavelength thick, or single wavelength tall, to run around the surface, in this case, rather than going down into the material. And so and what we can do is we time, the tester is going to time how long it takes for this wave to go and travel around and reach a back wall. And then that's going to bounce off the back wall and make its way back, back to our tester. Okay, so it's a pulse echo. It's a pulse echo shear wave running along the surface, and so it only goes that the surface wave property. What that allows us to do is, if you imagine that we have a break or a crack. Whoops. Slide. If we have a break or a crack in here somewhere along the part, right, now our wave would reflect off of that crack or that break, and so it wouldn't take as long. We would get a return echo sooner than it would be if it was going all the way to that back wall at the bottom left corner there. And so it can be used for that. So it's often used for long kind of materials that run for a long distance. And maybe are in areas where they're hard to get. So the most common form of this used is for oil and gas pipelines that run underground. If you have an area of the pipe that's exposed, right, you have like a little trenched area, and then you can send this wave down, and it doesn't matter that the pipe or whatever is buried underground. And aircraft, where these have been used before, is you can run this along like a wing spar. So if you can access the wing spar out in like a fuel tank in the wing, but you're trying to inspect where the wing spar, like what's called the carry through, where it runs through underneath the fuselage, instead of having to get access to it all inside the fuselage, you can send one of these surface waves along the top of the wing spar, along the bottom of the wing spar, to inspect the areas where maybe it goes through the belly area of the fuselage and it's harder to get to. So we can see things that we don't necessarily have direct access to by using this technique. And again, this is a very specialized technique. It's not something you're going to see very common, and you would pretty much be a level 2 or a level 3 qualified technician to be performing this kind of stuff, because it takes a lot more setup. It's interpreting the results, whether it's a relevant indication or a non-relevant indication or a flaw isn't as obvious as in kind of the standard forms that we're going to do, like pulse echo and that kind of thing. So that kind of finishes up those. We didn't quite get to them. Now we're going to start looking at the equipment itself. So the first thing is looking at our different transducer types. And so there's kind of 5 main categories we've got here. And some are more of an adaptation of others. So we've got the top left there, straight beam, and then angle beam we've talked about. Delay line is something that it's called a fixed delay. We've got some delay line probes, and it's basically a straight beam that's offset from the part a bit, and they're used for finding surface cracks. There are some cases where you have a dual element probe that's shown in the top middle picture there. So within the same probe body, you've got a driver and a pickup coil side by side, and they're kind of set at a slight angle to be able to see that. Here's our delay line probe to the right, where we've got a distance where that near field. Remember, we've got a lot of interference, and we can't accurately see things at the near field. That's going to take place in that delay block there, kind of the clear blue part that I have highlighted right now. And then we can look at our what's going on down in the part below that. And then dual element or through transmission is shown here on the bottom left. Okay. And that's where, rather than bouncing sound off of the back wall or off of a flaw, we're going to see if it gets attenuated, or if for some reason it's blocked from traveling through the part. So if you have a flaw, your sound's not going to travel from one side to the other. Immersion testing is shown here. That's where you, instead of using a coupler that you put on the part, you're going to have a bath. And then down at the bottom, I've got array. An array is, we looked at eddy current arrays. So an array is multiple transducers all in a single probe body. And it can be used for things like mapping. They can actually produce 3D type images that are can be pretty accurate, pretty cool to see. So just again, some of the kind of how these are laid out. So here's a straight beam reflective probe looking at a flaw. This is what we're going to do in class. Angle beam transducers. And what we need to know, what's important about angle beams is we have to understand the sound path. You have this angular distance, right? It's going to be longer than the part is tall, for instance. And so you have to have the angle of refraction, and you have to tell your, the theta sub r there. You have to tell your your tester, the device that's doing the testing, basically what that angle is. So the probe itself here, up at the top, is at a certain angle. Right, so we got our probe at a certain angle right here. And then that changes. You have a different angle that the sound actually takes once we get into the part. And so part of setting these up is we have to calibrate, we have to figure out what that exact angle, that sound angle is that it's taking. We have special calibration blocks that essentially kind of look like this, where there's a known hole and a surface distance, and then what they would have is along the top, there'd be graduations. And so you move your probe, if this was a calibration block, you move your probe left and right, and it would tell you if the edge of your probe is at a certain hash mark there, it would say it's 45 degrees. Or if it's at the 60 degree mark, then your angle of refraction is 60 degrees or 20 degrees. So the calibration blocks are designed to help you figure that out. And then you can kind of figure out your distances from there. So this gets into, you got to kind of you have a basic understanding of trigonometry if you're going to be doing angle beam testing, because again, the path the sound takes is going to be different than the surface distance or the depth of what's called the depth of what they call the first leg. And what I mean by first leg is if we have this and if we were to move this probe over, say we had our probe sitting here, okay, the sound is going to take that refracted angle and it's going to hit the back wall, right? That's our first leg. And then from there, it's going to bounce and it's going to continue kind of at the opposite angle till it goes the other way. That's our second leg, right? And then at some point, it's going to come in, it's going to hit here, there's our third leg, and then on this part, it's going to come off like this, right? And then it's going to start going like this. So you see how that can get really complicated when you get these weird angles in there? Where the sound starts bouncing all over instead of a nice straight out and back. But then once we get to, so you really won't get much of an angle. If my probe was over to the left where I drew, you're not going to get much return right away. But now where they show the part there where the probe is in relation to that simulated or that flaw, now it's going to get a return signal. So you often won't get a backwall echo or any kind of a return signal until there is something in front, until you do find a flaw. Okay? Versus what we're going to get used to, where there's always a backwall echo when we're doing straight beam testing or transmit receive or reflection probe type testing. So here's where angle beam testing is often used. So you can see in this case, you can't go directly on top of this, the weld, because it's not a smooth surface. You wouldn't be able to get a good acoustic bond between a reflection probe and this. So they're going along. So what you can see here is on the screen, in this case, they are showing a flaw. That's what a flaw would look like. If you're in a non-flood area, there would be almost nothing on the screen. It would be, you'd have a little bit of the little peaks down at the bottom, but you wouldn't have anything else on the screen. Dual element transistors, they look a lot like a standard reflection transducer, but in this case, we've got two separate crystals in there, a transmit and a receive. Okay. And you can see the sound is sent in such a way that it refracts and reflects back, so that it comes from one transducer, returns to the other side. And they're slightly angled towards each other. And they're good they eliminate some of that near field interference. Because the near field interference is you have the sound waves leaving the probe, you have the sound waves returning, and where they're hitting each other. We saw the video on acoustic interference. It can cause some waves to cancel each other out. It can cause others to you've got where they build on one another. And so by not having the transmitted sound and the return sound intersect with each other, you limit a lot of that interference that you get in the near field. And so they're designed for near surface, or in this case, it's showing corrosion. And so you can use this to find corrosion on very thin parts, like say a sheet metal skid, for instance, where normally, oftentimes we'd use eddy current for that. This does allow us to look at sheet metal. It also is, it's got that thinner metals, basically, is the big advantage of these. Disadvantage is you do have to take into account, you can see there is still a certain amount of refraction taking place, and so the probes have to be matched to the material that you're using them with. Okay, you have to have where a standard probe that's a single driver pickup element, piezo element, that's performing transmission and receiving on the same crystal, since it's going straight down and straight back up, you don't get any refraction. But something like this, where you have to have a focal point, it's got to be tuned to the material that you're using, and it's got to be tuned to the thickness of the material that you're planning on using it on. So they tend to be more application specific versus the probes we have that are. When you start testing, we're going to have kind of 4 different modes that are out there. And so there's A, B, C, and D scan, and these are kind of the definitions of them. So A is what we're going to be doing, and then B, we have on our newer tester, it can actually do kind of a simulated B scan. It can't do a true B scan, but it can do a simulated B scan. C scan is where you start to get a 2D representation, kind of like a heat map, where you can, especially if it's different colors or different densities. And then D scan is what you think of. So C scan is like if you've seen if you've ever had an ultrasound test done, ultrasonic test for like medical reasons. If you're getting tissue like tendons looked at. Or you've probably all seen ultrasounds of babies, of in vitro. That's a C scan type, where it's a 2D picture. And then D-scan is a 3D visualization. And there are 3D medical ultrasounds now too. People see with babies and that kind of, but we can do that on materials. So what do these look like? So here's a scan, and this is what we're going to be doing. And so you can see the probe here, the transducer, and the screen are basically the same thing, just one turned on its side. Okay? So if we were to take this, if we take this right here and kind of turn it on its side, we'll get this crack echo right here is this side over here. Okay? And then the back surface echo is the left side of that. And so that's what we'll be looking at with our testers in our lab. B-scan is where now we can kind of get a side profile. And what the key is, so we've got essentially here the same part with an A-scan on the left, a B-scan on the right. It gives you a depth over a distance. But what you have to have is, in order to do a B-scan, you can see here, we have to be able to translate movement of our probe to movement across our screen, from left to right here. And so the probes, like the probes we have, just a simple probe, if we wanted to do a true B-scan, we would have to have what's called an encoder, basically a little wheel put on the side of it that as you slide the probe along, that little wheel turns and it tells your tester how far you've slid the probe. Right? Because otherwise it has no idea when you move the probe left to right how far it is, right? So that's where we're limited to A-scan versus a B-scan. It's kind of like the measuring wheel. Does anyone seem like they measure the ground with those wheels around? It's similar to that. The next type is, so B-scan is shown here, and this shows a B-scan with other things. Then if we take, so a B-scan, that's basically a line. What they're showing is, on this B-scan here, what was created is a transducer was run from this end, from kind of the bottom left to the top right. And so as it's going along, it's going to send pulses. You know, it does a pulse here, it does a pulse here, it does a pulse here, it moves across. If we take that same kind of line and we start to move it this way as well, then we get a 2D array. And that allows us to do a C-scan, which gives us that two-dimensional top view. Which will look like a heat map. And that's shown on the bottom right here. So this shows a C-scan, okay, of a part. So this is a single probe where they moved in kind of a grid search pattern, okay? And you would have actually had to have two encoders put 90 degrees to each other. Okay? And so one encoder is measuring the movement of the probe, we'll say front to back here. And then the other one, every time it's moved from left to right, then it has to track how far it's moved left to right, and then the fact that, it's moved back, and then across, and then over. So you can see it kind of does this zigzag search pattern. And what you get is this view on the right. And what they're showing here is, that's what I mean by a heat map. And so it kind of says, okay, there's a flaw. It'll show you the different flaws, and the colors represent the depth. Okay. Or the conductivity. If we take that and kind of turn it up on an angle, and oftentimes this is done with an array type probe, we can get a D-scan indication. And that's that 3D view that I was talking about. So this is the probes on the top of the material. This is looking at the bottom surface. So in this case, you've got some holes, 3 holes sticking up from the bottom. Okay. You've got a slot or a cut on the right side there, kind of coming up. And the probe, you can imagine, the probe's not shown here, but the probe would have been sitting somewhere above this, somewhere up here, and it was bouncing sound down. Okay. So this is looking at kind of the backside. So this works a lot like, it's very similar to the D scan that we saw with eddy current testing, where they use that array probe to do it. But now we're using sound instead of that. Some other ways we can do these with phase array. So our normal V method at the top, we're scanning what's called a mechanical scan. We're moving our sensor. But there are some different ways that we can scan an area to get these B and C scans with either a single probe or multiple probes. So what you see here, the second one is we've got phase array method using what's called sector scanning. And that is the probe itself, the transducer, doesn't send a beam straight down. It can adjust the angle a little bit. And so it actually sweeps in like a cone. So it'll start, say, in the middle, and then it sweeps out, sweeps out, sweeps out, sweeps out, sweeps out. And it can kind of do a two-dimensional form doing this. And it has to track its angle and all that stuff. So that's one. The other one shown here can actually be done for 3D scanning. And this is showing what's called a matrix array. And so here you've got multiple transducers, a matrix array, that are all kind of doing that sweep function, like what's shown in the middle. And you put that all together, you can start to, now because you've got multiple sensors kind of hitting each other, kind of looking at the same spot from the side, you can start to actually get that three-dimensional mapping of it, rather than just a single one that looks at height differences.